Welcome to today's breakdown. Have you ever stopped to wonder what exactly happens behind the scenes when you click a link or send a message across the internet? I mean, it feels instant to us, right? But there is actually this entire, completely invisible, microscopic journey taking place in milliseconds. So let's dive into this. Today, we're going to act as network detectives. We're going to track a single, tiny data packet on a mission to deliver a message across the network, and we'll uncover the invisible magic of exactly how computers talk to each other using something called the Address Resolution Protocol, or ARP for short.
Here's our roadmap for this deep dive. First, we'll meet our network topology. Second, the three essential tables. Third, host A finds the router. Fourth, the router finds host D. And finally, Number 5, the fast return trip.
All right, section 1, meet your network topology, setting the scene. Okay, so here's our network setup. We've got 4 hosts in total, 2 switches named X and Y, and 1 router sitting right in the middle, splitting our world into 2 completely distinct IP networks. Specifically, we're going to be focusing on host A at IP address 11.11.11.10, the router's left interface, which is known as ETH1, at 11.11.11.1, the router's right interface, ETH2, at 22.22.22.1, and our ultimate target all the way on the far side, host D, at IP 22.22.22.40. Now, what's really fascinating here is the dual address system. Every single device has a logical IP address, which you can think of like a neighborhood zip code, and a physical MAC address, which acts like the exact physical front door to your house. You need both to deliver a physical letter, right? Well, the exact same logic applies to network data. Moving on to section 2, the 3 essential tables, the detective's address books. So how do our devices actually navigate this neighborhood to find those specific doors? Well, they rely on 3 critical ledgers. Let's break this down. First up, the ARP table maps an IP address to a MAC address, and it's used by layer 3 devices like routers and computer hosts. Next, the MAC table maps a specific physical switch port to a MAC address, and our switches use this to direct local traffic. Finally, the routing table maps entire IP networks to egress interfaces on our routers, literally telling the data which exit door to take. But here's the absolute crucial point. While the routing table is pre-populated, meaning the router already knows which of its physical interfaces connects to which logical network, the ARP and MAC tables are blank slates. They're totally empty when a device turns on, and they have to be dynamically filled in as traffic actually moves around the network.
And that brings us to the absolute star of today's show. ARP, or the Address Resolution Protocol. It's the protocol that bridges Layer 3, our logical IP zip codes, and Layer 2, our physical MAC address stores. It does this by dynamically mapping a known IP address to an unknown physical MAC address. ARP is the essential tool our devices are going to use today to solve the mystery of physical hardware locations. Basically, if a device doesn't know where to send a packet physically, ARP is the protocol that figures it out.
Section 3. Host A finds the router hitting the first roadblock. All right, picture this scenario. Host A has some data it desperately needs to send to host D. It already knows host D's IP address is 22.22.22.40. Looking at its own IP, host A immediately realizes this destination is on a completely different network. So to get there, it knows it has to send the packet to its default gateway, which is the router. But there's a problem. Host A knows the router's IP address 11.11.11.1, but it does not know its physical MAC address. It has hit a massive roadblock because physical local networks strictly require a MAC address encoded in a Layer 2 header to actually deliver the data to the correct piece of hardware. It's literally stuck. So what does a good detective do when they need information? They ask. Host A effectively pulls out a giant network megaphone and shouts an ARP broadcast to the entire local network. Who has IP 11.11.11.1? It's broadcasting this message absolutely everywhere locally because it doesn't know exactly which wire the router is sitting at the end of.
Let's trace the exact steps here. Step 1, host A broadcasts that ARP request. Step 2, switch X receives this broadcast and floods it to all of its active ports, except the one it just came from. It's like it's passing the megaphone message down every single hallway. Step 3, the router hears this message, checks its own IP, recognizes that it is indeed 11.11.11.1, and replies directly back to host A with its physical MAC address. Boom! Mystery solved. The missing piece of the puzzle is acquired. With that crucial piece of information, look at what happens next. Host A can finally build the Layer 2 header.
We've got the source MAC, which is host A, and the destination MAC, which is the router. Host A successfully wraps up the data packet with this brand new header and forwards it down the wire through switch X straight to the router's physical door. Which leads us to Section 4. The router finds host D. Passing the baton. So the router receives the packet on ETH1, strips off that layer 2 header host A just made, and looks deep inside at the destination IP. It checks its pre-populated routing table and says, 22.22.22.40, I need to send this out of my ETH2 interface to reach host D's network. But wait, plot twist. The router is now facing the exact same roadblock host A just did. It knows host D's IP address for sure, but it has absolutely no idea what host D's physical MAC address is. Once again, the physical layer 2 information needed to complete the delivery is completely missing. Now, you can probably guess what happens next, right? It's a visual callback to our earlier roadblock. The router pulls out its own megaphone. It shouts an ARP broadcast out of its ETH2 interface into the second network. Who has IP 22.22.22.40? It's the exact same ARP detective work, just happening on the other side of the neighborhood. Step 1. The router broadcasts the ARP request into the new network. Step 2. Switch Y, just doing its job, floods that broadcast to all its active ports. Step 3. Host D receives the request, says, hey, wait, that's my IP address, and replies directly back to the router with its physical MAC address. And just like that, the layer 2 header is rebuilt. The brand new header has the source MAC as the router's ETH2 interface and the destination MAC as host D. The router wraps the data in this new header and successfully delivers the packet to host D. Once it arrives, host D strips off both the layer 2 and layer 3 headers and finally gets to process the actual data. The baton has been passed and the initial delivery is a total success. Finally, Section 5, the fast return trip, a smooth journey home. Okay, now host D needs to send a response back to host A, but this time the network is already prepared. That first trip was kind of clunky and slow. It relied heavily on noisy ARP broadcasts and required stopping constantly to gather information to build and rebuild headers. But the return trip, it is lightning fast. Why? Because all of those ARP, MAC, and routing tables we talked about earlier are now fully populated. The devices have dynamically cached those IP to MAC mappings in their memory. They don't need to ask anyone where the doors are anymore. They already have the addresses written down. Let's follow the packet on this completely frictionless return journey. Step 1. Host D already knows the router's MAC address from its cached ARP table, so it builds the headers instantly and sends the packet straight to switch Y, which forwards it directly to the router. Step 2. The router already has host A's MAC address cached, so it immediately swaps the layer 2 header and sends it straight through switch X back to host A. Step 3. Host A receives and processes the response. No megaphones, no shouting, no waiting, just pure, incredibly efficient networking. 30. That is approximately how many invisible steps it just took simply to send and receive one single piece of data across two very basic networks. From checking tables to flooding broadcasts to stripping and rebuilding headers, it really highlights the incredible unseen efficiency of everyday networking. Your computer, your switches, and your router are doing this ARP detective work constantly, caching the results and moving on in absolute fractions of a millisecond. The next time you click a link, stream a video, or send a quick text, will you think about the incredible ARP detective work happening behind the scenes? The invisible megaphone shouts, the dynamic address books filling up in real time, the constant stripping and rebuilding of data headers. It is an entire microscopic world operating silently and flawlessly just beneath your fingertips. Thanks for joining me on this deep dive today, and keep learning.
If this helped you, subscribe to Packet Fixer for real-world network troubleshooting.